Everyone. Welcome to this week's Crunch seminar. And to begin with, this week we have both the talks from speakers from Crunch department. Our first talk is by Leonard Gleyzer. He would be talking to us about a review of diffusion models. Leonard is a second-year PhD student in the Department of Applied Mathematics here at Brown, working with Professor George Karniadakis, and he's interested in interdisciplinary application of scientific machine learning. With that, let's welcome him. And let's all wish him a very happy birthday.
Thank you. Thank you very much. Okay, so I'll just go ahead and share my...
Yeah.
Okay, can everyone see this full screen?
Yes, yes.
Okay, so hi everyone. I'm Leonard. So today I will be presenting a overview of diffusion models. So most of you have probably seen diffusion models in media or social media appear, perhaps things like this where people put in a fun textual description, such as a gentleman.
Leonard, sorry to interrupt you, Leonard, but the screen, at least on my computer, is very small. Is that true for some data? Is it?
I see a band of it. I don't see the full thing, but I see a band.
Maybe this will be better if I don't full screen.
It's bigger. Yeah.
Do you see the full slide?
Actually, Leonard, we are seeing this writing very small, the one that's below this brain image. That's too small. Is there any way you can increase the resolution?
I can make it bigger, like this.
Okay.
But it's just a textual description for this generated photo.
Okay.
But yeah, so a lot of you have probably seen these kind of fun images in media where people put in text descriptions ranging from like pretty simple text descriptions like the 19th century otter portrait to full paragraph, very detailed descriptions like this techno alien robot on the right. And the model behind all these are diffusion models. So what are diffusion models? So at a high level, how do they work? So diffusion models are a class of deep generative models that have become very popular recently, and they work in two phases. So the first phase, or the the forward component of the diffusion process, sequentially adds Gaussian noise to a vector from the distribution that you're interested in. So with each successive step, more and more Gaussian noise is added until excuse me, until at the end you have basically pure noise. And then in the reverse process, a network is trained to undo this diffusion process. So to start from noise and then sequentially remove noise step by step until at the very end you have an uncorrupted image or vector sample from whatever distribution it is that you are interested in. So in a little bit more detail, so the forward process is you start with an uncorrupted vector. In the examples I've shown, the vectors are images. That seems to be the most popular use case for diffusion models currently. And so you start with this uncorrupted vector and you run a diffusion process. So in the case of these models, it is a discrete time Markov chain with the chain transitions being set to conditional Gaussians. And this lends itself to a simple parameterization because of the properties of Markov chains as a product of the transition kernels, so which themselves are normally distributed. And the variance schedule, these betas, is a time-dependent, the time-dependent variances that can be learned or fixed ahead of time, can be set as a hyperparameter. And a proper variance schedule ensures that xt for big T's, the final step is approximately an isotropic Gaussian. One popular parameterization for the variance schedule is a geometric decay. So that's the forward process Markov chain where you add Gaussian noise. And the reverse process is where the actual learning occurs. It's where the neural networks optimize. So you start with pure Gaussian noise, and then the model learns the joint distribution of the reversed Markov chain. So whereas in the forward process, the noise was added in each sequential step, in the reverse process, the model learns to undo the noise. So in particular, the model learns the time-dependent parameters of the Gaussians, so the mean vectors and covariance matrices. So what does the actual training of this look like? So it's at a high level, a maximum likelihood problem. You want to maximize the likelihood of the training data, or equivalently minimize the variational upper bound on the negative log likelihood. So this is technically an upper bound, but in the literature, it's often called a variational lower bound. So likelihood maximization here. And something to know, something of an important part of this is that it's possible to cast this desired bound in terms of a sum of KL divergences across the different diffusion steps between the Q distribution, so the forward distribution, and the reverse distribution. And the derivation of this is kind of messy, so I'm not going to go into it here. If interested, it's in the diffusion model paper. But the important thing to note, the key takeaway here is that all these divergences are between Gaussians. So this allows for analytic closed form expressions for this loss function rather than needing to use Monte Carlo estimates. So diffusion models are very flexible. Really, the only necessary condition is the dimensionality has to match on the input and output vectors, but the architecture choices, the parameterization choices are open to be kind of whatever you want them to be. So in the forward process, we can treat time-dependent, the variance schedule as time-dependent constants. So the L of big T is a constant and can be ignored. As for the parameterization of the functional form of the covariance, the authors found that a simple covariance parameterization where the time-dependent covariance matrix is product of independent Gaussians with constant scaling, where the variance scaling is the variance schedule, the betas. And this lends itself to a simpler parameterization of the intermediate loss terms, where it's can be expressed as the square difference between this function mu tilde and the parameterized mu sub theta, where mu tilde is a function that depends on xt, x0, and the variance schedule beta of t. The actual form of it is not important here, but the important takeaway is that this parameterization lends itself to a simpler form for the loss terms. And the authors also
But
found that
Leonard, the mu tilde is known or not?
the mu tilde is known. That's it has a closed form. It's not something that's learned.
Okay.
And the authors of the paper found that training mu theta, so the parameterization of the mean of the process, they trained it to really predict the noise component of the process. So the actual parameterized component of mu is parameterizing the epsilon. So taking the parameterized epsilon, the parameterized noise, and then scaling it with betas and these alphas that depend on the betas, they found that this yields pretty good results. And then manipulating the loss function to reflect these choices found that training became stable, and we led to better results. So as for the training and sampling algorithms, the actual vanilla diffusion model for training and sampling is pretty straightforward. Like it's incredibly flexible. Again, the only requirement is the input and output have equal dimensionality. But for the training part is you sample an uncorrupted vector from your distribution, sample your time, step, and noise, and take gradient descent steps on the previously mentioned loss function until the model has converged. And then for sampling process, you sample Gaussian noise, and with the train model, remove noise sequentially until you have a sample from the training distribution. So this is a very flexible framework to generate new samples from a distribution of interest. And so those were, so that's the vanilla diffusion models. But what people have been working on, and what you've seen, like the text generated images, are conditioned diffusion models, where you guide the diffusion process based on some class label or some image or text embedding to guide the diffusion process toward a particular subset of the distribution that you're interested in. And there are different variants of this. There's classifier guided diffusion. So by training a second classifier network to guide the diffusion process conditioned on class labels is one method, one option in the Glide paper. That was a popular one. There's also classifier free guidance. So training a conditional model together with an unconditional model and having one kind of guide the other. That's Imagine. And there are also other forms of other popular architectures of guided diffusion. So there's DALI 2, which uses something called the VQ-VAE, so vector quantized variational autoencoder. There's also Midjourney, different ones seemingly coming out every week that continue to show state-of-the-art results. And in some way, it seems that these models are able to sort of, in some sense, interpolate in a latent space of human imagination. Is one way to see it. Like we can picture things that we've never seen before in our life, and we can imagine them, and these models seem to be able to kind of emulate a similar process. So another popular sort of trend in diffusion models is scaling up the diffusion models. Now, as powerful as they are and as cool as the results are, actually training and sampling from the diffusion model is pretty computationally expensive. It can be pretty slow. You need lots of good GPUs to get really high quality generations. So there have been a couple of innovations in the space of scaling up these diffusion models. One of them is cascade diffusion models. So which is a pipeline of many sequential diffusion models that generate images of increasing resolution. So rather than having one giant diffusion model on a very high dimensional space that would be intractable, cascade diffusion models generate a lower resolution image, then use that as the conditioning for the subsequent diffusion model to upscale it and upsample it and keep going sequentially like that. One of the most popular scaling up of diffusion models is what's known as latent diffusion models, where you learn a projection of the high dimensional space that you're interested in to a lower dimensional latent space and run the diffusion there in the lower dimensional latent space, and then upsample from the lower dimensional latent space back to your original space. And the most popular one of these latent diffusion models you may have heard of is called stable diffusion. So you have this latent space diffusion process with bells and whistles of conditioning, self-attention models, denoising U-nets, cross-attention, skip connections. So, you know, lots of training tricks and methodologies to get this to work and be well stable. And as a little aside, Stability AI, the startup behind Stable Diffusion, has recently announced that it's received $101 million in venture capital funding to develop these content generation diffusion models, not just for images, but also for audio, 3D, movies, natural language. So it seems that there's a very large market for AI-guided content generation of various sorts, and the same VC firm projects that Stability AI can be valued at $1 billion or more. So AI-guided content generation, new paradigm, very popular. Lots of interesting possibilities. I'd also like to mention that there's a continuous time extension of diffusion models where you use a stochastic differential equation to define a continuous time diffusion process. Use this SD to corrupt your image into noise, and then learn to solve the reverse SDE to generate the image. And learning these differential equation SDE solvers is its own many different methods and fields and research ideas there, but not as popular as the discrete time diffusion models, but still gaining traction as a continuous time extension. Now, most of the popularity and mention of diffusion models.
Leonard,
so
can
far,
I ask a question here? Because for the continuous case, so we have the option of also having jumps right in the noise, like Levy noise. Has anybody tried to do that in these models, or because of the tractability of the Gaussian noise, people are just doing Gaussian noise? Because you can bias, you can have, basically you can have memory in the process, right? Yeah.
Yes. So I'm personally.
Is it all Markovian? That's what I'm asking. Is it all Markovian? Or there's no Markovian too?
I am not sure, to be honest. I haven't looked into the continuous time analogs too much, but There are non-Markovian versions of neural ODEs and neural STEs, so I imagine that it would be possible to have some kind of non-Markovian or non-Gaussian bias, or with jumps and Levy processes as well.
Okay.
So most of the diffusion models have been so far, the ones that people have seen have been in the space of media and creativity, but this is Crunch Group. We're more interested in the applications to scientific domains, which they're definitely a lot less. So diffusion models themselves, and at the scale they are now, is very new. So diffusion models in scientific domains, there's even more of a sparsity of research areas there. But I did find a couple of interesting papers that to mention the scientific domain. So the first one is diffusion models for medical anomaly detection, published at the beginning of October, so this past month, about a month ago. And the idea is to use classifier-guided diffusion for image-to-image translation between diseased and healthy subjects. So, for example, a brain scan of a diseased subject would then be sequentially corrupted with noise to then yield an encoded noisy image, and then running a reverse diffusion process, so running the reverse part of the diffusion model to remove the noise and output what would be a healthy scan as the output, and then comparing the two to get an anomaly map. Now, this is very general framework. It doesn't only have to be in medical imaging. It seems that any sort of anomaly detection, it seems you can be able to add noise, then use the diffusion model to remove the noise and compare the before and after to get an anomaly map. I find this a very interesting use of diffusion models. Another one that I've seen, or that I found, this was published in iClear in this year's iClear conference. GeoDiff, geometric diffusion model for molecular conformation generation. So this uses a diffusion model to predict the 3D spatial geometric conformation of a set of atoms that are bonded together in some specified way. So to predict how they would exist spatially. Another diffusion model in scientific domains that I found very interesting, this was put on arXiv October 24th, so literally like a couple of weeks ago. So this is very, very new. And the idea is it's a conditional diffusion model where by conditioning on specific structures of protein targets, the diffusion model generates small molecule ligands that can bind to these specific protein targets. So targeted custom drug delivery and drug design is definitely a big open space for diffusion models to potentially shine. So those are 3 papers that I found. There really aren't a lot on diffusion models in scientific domains, so lots of possibilities there. Perhaps conditioning on PDE data, sensor data, physical information, combined with textual conditioning. So maybe something along the lines of design an airfoil to withstand such and such atmospheric conditions, and you put in that textual description along with perhaps some sensor data, and a diffusion model might be able to generate a schematic of said airfoil or a material with some specific desired properties. Again, the high flexibility of these diffusion models lends itself to vast exploration, lots of possibilities. So a couple of blog posts that I found very helpful in making this presentation, one on assembly AI, one on AI summer, have some very good resources on diffusion models and their extensions. So thank you. That is my presentation on a review of diffusion models.
Thank you, Leonard. Questions for our speaker? You have clapping hands from Sasha.
Thank you.
Maybe you need to unmute.
George, we can hear you.
You said Sasha has a question?
No, he clapped.
Oh, okay.
Probably I have one small question.
Yes,
So
please.
then if we go to the algorithm part, the assembling part, so you based on what I know is the diffusion model, usually the sampling is slow, right? It may take more than 10 minutes for sampling. But if I look at the code here, I'm not sure why it would be slow, because it seems to me just some equations commutation. So which step is slow here?
I think that the slow step is that you have to sample sequentially. So T can be very large, and you have to remove this noise in sequential steps, one after another. And for high dimensional data, and if your neural network is highly parameterized, that can use a lot of computational resources to sample.
I see. Okay. What's the standard value for T, which is capital T? Hundreds or thousands? Or?
Depending on the application, but it can, some simple models are 50 to 100, but the more advanced models can be hundreds, maybe thousands. And if your sample space is very large, if your images are very high resolution, if you're using a diffusion model with lots of bells and whistles, like subcomponents of self-attention or autoencoders, that also leads to computational overhead, because the algorithm itself is pretty simple and straightforward, but depending on the form of your parameterization and the neural network architecture that you're using, running those is sequentially for many time steps is what can be expensive.
I see. Thank you.
There's a question in the chat by Nicholas.
Yeah.
Nicholas, you can unmute and ask your question.
Sure. Thank you for the talk. My name is Nicholas. I'm a PhD student at Johns Hopkins. I was just wondering, in terms of the size of data that are needed for diffusion models compared to other models like GANs or VAEs, if you could comment a little bit on that.
So GANs, I know that GANs, they're not really used much anymore. They have a lot of training difficulties and instabilities. As far as the size of the data needed, I want to say that diffusion models require more data. But they have also, diffusion models have also been shown in a few papers to outperform GANs, VAEs, and other generative models in terms of the quality of the generation.
Great, thank you so much.
Hi, can I ask a question?
Yeah.
Yes, Zhang.
Yeah, hi, I'm Yixia. I'm a former PhD student at George Group. So you say that the only requirement is equal dimension of input and output, but I remember your first example is saying that you can like input a few texts and generate a movie. Is there anything I missed?
So the equal dimension of the input and output is for the unconditioned diffusion component, where you so if you're sampling from an image distribution and your and your images are 32 by 32 pixels, then your noise also has to be 32 by 32 pixels. The equal dimensionality doesn't apply to the conditioning data, which could be the textual description or the other data that are used to guide the model.
Okay, got it. Thank you.
I have,
Do we have? Yes,
Leonard,
George.
I have a question for you and for Zhang, actually. Can we replace our GANs with diffusion models in the functional prior?
I don't see why not.
Because we like you said, we had some difficulties in the training there. So Zhang is now doing like normalizing flows and other stuff. But Zhang, what do you think?
George, I'm not sure. So this, I think there are a lot of differences between GAN and diffusion models. For instance, for GANs, the latent space, the unknown space, does not have the same dimensionality as the dimensionality of the functions, the distribution. But diffusion model requires that, and also, like Lulu just commented, that the inference time is for diffusion model, it requires way more inference time than GAN. So I'm not sure. I think we can do that, but I'm not sure about the all the technical problems that may appear.
There is,
Yeah, it seems that
Leonard, there is a free code, right? Maybe we can try that. We can try to
code,
get some of the stuff.
code of diffusion models. Yeah, there are lots of libraries for different implementation of diffusion models with various optimizations.
I found one I think I sent you a copy to you and Raj is trying to create now a alien GK. Does that sound scary?
Alien GK. Alien George Kaniadakis.
I thought you wanted the Pixar one.
Oh yeah, the Pixar. Yeah, no, the Pixar. Yeah, not the alien. You're right, the Pixar one. more humanized version.
Leonard, I have a follow-up question. So could you comment on the other difference between diffusion model and GAN? For instance, the training complexity, the time complexity of training, the time complexity of the inference. I mean, in GAN we can do some prediction, right? After the
yes.
model is trained, but
So GANs. So I think GANs and GANs in both training and inference are a lot faster than diffusion models to reach their own definition of convergence. But GANs, they're being trained adversarially. They have their own issues of like mode collapse and different things and various instabilities. So they're not really. No one really uses GANs anymore for generative modeling because of these instabilities. Diffusion models are definitely slower and require more computation and take more time at inference. But the trade-off there is the quality of the generated data is much higher and more stable.
Yeah, and how about the requirement for the computational resource? So I've heard some stories. The training a diffusion model needs more GPUs, need more computational resource. Do you have any comments on that?
So it does use GPUs and computational resources. You pretty much need at least one good GPU to generate a high quality image or vector from whatever distribution you're interested in if the dimensionality is high. I tried to run a CPU version of stable diffusion to transform an image based on like a textual embedding, and on CPU only, it still took a lot of time. So GPUs are kind of necessary
Yeah, of
for
course.
diffusion model training and sampling.
Zogren, I think the latent, Leonard, can you show us the latent version, the one in the latent space that for high dimensional, because that would be very appropriate, I think, for the functional prior. This one here.
Yeah, the stable diffusion and latent diffusion models seem to be sort of the state of the art in scaling up diffusion models to higher dimensional spaces.
Oh, so in this case, the latent space does not have to be the same dimensionality, right?
No.
That's good. That's good.
So the first one, Leonard, you mean the super resolution, right? It's the same as super resolution, or
Yeah.
The transformers too. Okay. Zogren, I would suggest that we look into the second bullet for the functional priors.
Yeah. Yeah.
Hey, can I ask a question? This is Nat Trask at Sandia. Sorry, I joined a little bit late, so you might have already talked about this, but did you speak to the semantic map and the conditioning there?
No, I didn't.
Is this just listed as like one of the cogs in the machine?
It's just listed as one of the cogs in the machine. The conditioning can be really whatever you want to condition it on, depending on how you structure your model. So you can use text conditioning. So the conditioning is really just auxiliary data that you feed to the model to kind of guide in a certain direction. There's no real restrictions on it. So you can condition on text or text embeddings. You can condition on other images, condition on maybe audio. Stability AI, the makers of Stable Diffusion, are also developing something called dense diffusion to generate music and songs based on training data and conditioning. So the restriction on the conditioning data, there really isn't. It depends on how you want to structure your architecture and model.
But in terms of conditioning, this is like probabilistic. Like, is there a joint district, like the way you would do a VAE, that there's a joint distribution that you would build up a conditional decomposition of? Is it something like that?
On some level, yes. You are building up
right.
your conditional distribution.
Awesome, thank you.
Adam,
really good topic, Leonard. Thanks for a really good topic, and lots of people, 56, dial in to listen to you. So your birthday. So but really good topic. I really want us the Crunch group, to do something in this domain.
Yeah, it's definitely very, very interesting and underexplored field, especially for scientific purposes. There's really not much there.
Thank you, Leonard.
Thanks. Yeah.
So we'll move into our next speaker. The next presentation is a joint presentation by Quercus and Zhang from Crunch Group. Quercus, you want to go first? Then I'll introduce both of you, but you may want to share your screen.
Okay.
So they would be talking to us about from GRANT to GRAFF, PD and energy-based learning algorithms for graph neural networks. Quercus is a PhD student in the University of Zaragoza. He's doing his PhD in mechanical engineering. He has obtained his bachelor's and master's in industrial engineering. And currently he's interning with us at Crunch, advised by Professor George Kaniarakis. and Zhen. He is the final year PhD here, and he would be co-authoring with Quercus on this presentation. Thank you.
Okay, perfect. Do you see my screen?
Yes.
Perfect. So thank you for your nice presentation. So the title of our presentation is From GRANT to GRAFF, PDE and energy-based learning algorithms for graph neural networks. Okay, so first I will do a brief introduction about what graph neural networks are and the basics of geometric deep learning. And then we will discuss two good papers that came in last years, which are the GRANT and the GRAFF paper. Whoops. Okay, so first of all, let's introduce graph neural networks by the key concept of geometric biases. So most likely when you are engineering a solution in the deep learning field, you must take into account the data structure. So for example, if you have images, the correct way to process images, we already know that are convolutional neural networks, because they are especially engineered to exploit the locality of the features. So they exploit the structure of the data in a regular grid of minimal elements that are called pixels. Okay, so nothing new here. If you have temporal data, the same way you have evenly spaced snapshots of a continuous phenomena. So you can use recurrent neural networks to exploit the sequentiality of data. So in both cases, you are taking the advantage of, in some sense, the geometry of your domain. But what about if you have a more general data structure, like a social network, for example, where these kind of structures are not that well defined? So you can have random entities with specified relationships between them. Okay, so this is the generalization of these two. Okay, so these are special cases of this kind of structure, and as you can imagine, these are called graph neural networks, and this kind of structure is modeled in mathematics as a graph. So let's first recall what a graph is. So it's composed of two main components. So you have the vertices, which are the entities that you are studying. Okay, so here I have 5 vertices. And you have the edges. The edges are the relationship between the edges, okay? And these edges can be directed if the information flows from one node to another, or undirected, in which case the flow is bidirectional, okay? So in that case, instead of an arrow or a double arrow, we just represent it with a straight line, okay? And with this kind of information, we can assemble the so-called adjacency matrix. I think we all more or less know how this works. So the ijth component of the adjacency matrix is 1 if that edge exists in your edge set, or else is 0. So for example, for the node 1, we have in the first row, we know that the neighborhood of that node is node number 2, 4, and 5. So in this row, the second, fourth, and 5th columns have a 1s, and else 0. Okay, so this is the neighborhood of the node. The same way in the second node, and so on. And you also can define the degree matrix, which are the number of incoming edges to a node. So for example, in node number 1, we have 3 incoming edges, so the degree is 3. And it's a diagonal, obviously, because each node has its own degree. Okay, so what's the idea of graph neural networks? So graph neural networks are assembled in graph processing blocks. And there's a analogy between graph neural networks and multilayer perceptrons. In multilayer perceptrons, you have a vector and you multiply by a weight matrix, you sum a bias, and you activate by some nonlinear activation function, and you get another vector. And you repeat it sequentially until you get your final output. So in graph neural networks, it's exactly the same. You have an input graph, you process it with some prescribed rules, and then you get the first process graph. And you repeat it sequentially n times, and then you get your output as a function of the last graph. Okay, so this is the main picture. And it can be used in regression, classification, whichever problem you want to solve. Okay, so first, let's see how this information is processed. I'm going to present the graph convolutional network from KIPF in 2016, which was the most basic convolution generalization to graphs. So it consists on assigning a feature vector to each node, okay? And you assemble those feature vectors into a matrix, row-wise. okay? And this is called the vertex feature matrix. And you do convolutions over graphs, okay? So instead of an image, you do the convolution over the topology of the graph. And how is that performed? So if you see this operation here, if you multiply the adjacency matrix by the vertex feature matrix, you can clearly see that this operation in the normal matrix multiplication automatically gathers on each node the information of the neighborhoods. Okay, so this is pretty convenient because it's done, all the nodes are processed at the same time just by doing this multiplication. Obviously, this is taken literally from the paper. It's not as simple as that. Here you have the adjacency matrix include what? Sorry? Okay. So here the adjacency matrix, you have also the self loops. So here you will have ones in the diagonal. Here is the degree matrix, inversed and square rooted. This is for normalization purposes, because maybe a node that has degree 3, the flow of information, it's much greater than, for example, in node 5, which only has degree 1. So to avoid the normalization issues, you just pre and post multiply by these degree matrices. The H vector is the future vector. Here it's H because it's a hidden layer. And the W, it's a weight matrix. So this is the learnable parameter. This is where the backpropagation rule it's applied. And then once you have done this operation, you apply a nonlinear activation function, and you can add a residual connection here. Okay, so this is the simplest case of a graph neural network block. Okay, and you can see that it's permutation equivariant. So if you relabel the nodes of your graph, it still gives the same solution with that same permutation. So if the matrix A, you permute the elements of that matrix, and also you do that same permutation on the feature matrix, then the result will be permuted the same way. So that means that it's equivariant. And that's pretty obvious, because if you have a graph, it should be invariant under relabeling of nodes. So that's a good thing. And this is the simplest example, but we have plenty of algorithms which are called flavors of graph neural networks. This is the simplest one, the convolutional flavor, in which the weights, the convolutional weights are fixed, okay, are learnable, but fixed. Then you have another modification, which is the attentional flavor, where those weights are learnable, but also change depending on the sending and receiving nodes, okay? So this function, it's a variable function with respect to the income and outcome nodes. And this architecture was really famous because of transformers. If you recall the transformers paper, the title, it was called Attention is All You Need. So this is because the transformers are attentional graph neural networks, where here you introduce the positional encoding of the word embeddings. Okay, so basically a transformer is an attentional graph neural network. And then the third flavor, it's message passing. So in the message passing, that's the more general algorithm. So you can have an arbitrary function of the incoming and outgoing nodes, as simple as that. So those are special cases of the message passing algorithm. Okay, so now that we have the basics of graph neural networks, let's start with the first paper, which is called Graph Neural Diffusion. Okay, so what is really cool about this paper is that it makes an analogy of graph convolutions and solving an underlying PDE, an underlying diffusion PDE. So this is slightly related to the first talk. So let's see how it works. The key idea is solving the diffusion equation in a graph, basically. So diffusion equation, we already know what's the form. So we have the time derivative of a feature vector. In the heat equation will be temperature, but in a deep learning case, you can have whatever features you have. It's equal to the divergence of a parameter, which is called the diffusion parameter, times the gradient of that vector. So there's a special case in which the diffusion parameter is homogeneous and isotropic, so you can factorize it, and you can simplify the divergence of the gradient is still Laplacian. Okay, so we get this homogeneous anisotropic diffusion equation, which has two main comments. So first of all, it's a gradient flow of the Dirichlet energy. So if you define this energy functional and you do the gradient flow of that energy, meaning that's the continuous version, so to speak, of the gradient descent, you will achieve the same solution as this equation. Okay, and Zhen will later explain this more in detail, because you can generalize this to any energy function. And also it has a closed solution. So it's basically a Gaussian filter. So these kind of equations were really famous in the image processing world, as Leonard also said in the previous presentation, like a stable diffusion. So it's this kind of diffusion models are really useful in the image processing, because they are kind of like a Gaussian filter. And if you use a anisotropic diffusion constant, you can avoid edges in the image and so on. Okay, so but we want to make the analogy of the diffusion equation in a graph. So the diffusion equation in principle is continuous and the graph is discrete. So we should define the differential operators over the graph. Okay, let's find the gradient. The gradient will be defined as the difference between the future vectors. Okay, so here, this is taken from the paper, from the grant paper. However, it's a slightly different annotation between this paper and the next paper. In the next paper, in the GRAFF paper, they divide here by the square root of the degree of the node, just for normalization reasons, okay? But the idea is the same. Then we can define the divergence. So the gradient was an edge-wise computation. The divergence is a node-wise computation. And basically, it's gathering the information of the neighborhood edges, basically. And the Laplacian, which is the divergence of the gradient. So you have this weight sum of the difference of the future vectors. Okay, so now that we have the main differential operators, we can include them into the diffusion equation.
Sorry to interrupt you. There's something subtle here that I want to highlight, because there's something wrong with the original Grand paper. So this isn't a criticism of you, it's a criticism of the original paper. A requirement for this to be Laplacian is that the AIJ has to be associated with a SPD matrix. So it's not just any AIJ. It has to be AIJ is equal to AJI in order to get the Dirichlet principle that you had on the previous page. And so as you go forward, they're going to claim that attention is a valid AIJ, but attention is not. So the claims don't actually go through from this paper.
Okay, so maybe in the same part of the graph, he will explain it in more detail, because I think that in that case, they assume that it's a semi-positive definite, and yes. That's why I said that there's a slight inconsistency between the grant paper and the GRAFF paper, but it's just details. Okay, so let's have the discretized diffusion equation. So we have the time derivative equals, so here we have the diffusivity, this matrix, the gradient, and the sum, it's for the divergence. Okay, so if you can recall the previous slides, it's a tensional flavor. So this is like kind of a tensional neural network. Okay, and because it's nonlinear, we have to discretize in time. So the first approach, it's you can have a forward Euler scheme, so a first order finite difference scheme. However, they claim that you can use not only explicit but also implicit solver, or you can have higher order solver like Zhang. Okay, but for simplicity, for the sake of simplicity, I'm just sticking to the forward Euler scheme. Okay, so this is the final equation. So the next, well, let's see the matrix form, which is a simplified, not a simplified, but a compact way of writing this equation. So we have that the futures at the next time step is the identity matrix times 1 minus the step plus the step times a kind of adjacency-like matrix, which is the diffusion matrix. Okay, and they claim in the paper that if you make it time independent, that means that they have shared parameters. Okay, so it doesn't, when you do the convolutions, they all have the same shared parameters. So the parameter count decreases a lot. If you did a time dependent, you will need a different set of parameters for each time evolution of the diffusion equation. So that will be more expensive. But if you suppose time independency, those weights are shared. Okay, and so let's recall all the grant algorithm. So you first set the initial conditions, you have the input features, you embed it into a latent space, okay, with this probably nonlinear function, and you get the starting position of your diffusion equation. Then you solve it, you get the evolution of the features at time equals capital T, that is the initial conditions, plus the integration. So in the case of a forward Euler is this scheme, but you can choose whichever integrator you want. And then finally, you get the output by the reverse map, well, kind of a reverse mapping you get from the latent space back to your output space, let's say. And those are the learnable parameters. So you learn the encoding, the decoding, and also the diffusion matrix. That's the key point of all of this. And well, they tried this architecture in several benchmark graph neural network benchmarks. So first, we have the graph convolutional network. Then we have the attentional neural network. And here they have three variations of the grant with linear, nonlinear, and nonlinear with rewiring. Rewiring means that the adjacency matrix changes on its depending on the features of the graph. How are the features evolving in the graph? You can take off edges and put additional edges just to favor the flow of information over the graph. Okay, so here they get some state-of-the-art results. And also there's additional advantages. So they claim that it's robust against bottlenecks and over smoothings. So bottlenecks means that if you have a very big graph and you have nodes which are degree 1 or low degree nodes, the information won't flow as easily for those nodes. So we'll have like bottlenecks inside your graph. Okay, and the over smoothing, it's something like if you have a very deep graph neural networks, you will get your features very smooth. So all the features will tend to have the same value. So you get no information about that. And I think Zhen will say something about this in the next paper. So this enables for new architectures based on implicit schemes, but also on explicit schemes or more efficient solvers, higher order solvers. And the most important part, that they have theoretical guarantees. So because you are interpreting your training process as a partial differential equation, you can have all the stability theorems of the convergence theorems of classical PD theory and analysis theory. So that's always a good thing. Well, and also I didn't mention this figure. So the bottlenecks and over smoothing in the continuous line, they have the diffusion networks with the increasing number of layers, and the accuracy, it's almost the same. And in these continuous graphs, you have the normal without the diffusion. So you can see that when the more layers you add to the model, the less accuracy you have in the model if you don't have this diffusion model.
Can I make a comment here? Because so going back to my last comment, the consequence of that is that there are no theoretical guarantees, right? You can't prove stability in the setup. So you didn't go into the specification of how they weight the graph, right? But if you use an attention mechanism for that, then you lose all the theoretical guarantees that they claim.
Yes, and also there are several proofs that they assume only linear activation. So I think that Zhen will have some comments about this. because yeah, let's talk about this a little bit in the GRAFF paper, because it has more interpretability in some sense, because it's energy based. So, but yeah.
Also, Quercus, I think here for the plot, the solid lines, I think, correspond to a high order discretization of the, because just the Euler is the one that after layer 3 or 4, the accuracy goes right down to, but the solid lines correspond to the high order discretizations, as I recall from the paper.
Okay.
Otherwise,
Nah.
right, the standard
sure.
the standard neural network is the explicit Euler.
Yes.
If you look at the figure caption, you will see.
The standard neural network here in the discontinuous is the graph convolutional network from KIPF. And so the discontinuous line are a graph convolutional network and graph convolutional network with residuals.
Do you have the caption? I have the caption of this figure. I think the solid lines correspond to high order. If somebody remembers or he has,
okay,
maybe you can.
yeah,
that was sort of the point actually of this because I used this before. So,
oops. Okay, so maybe I can look it. Oh, because if I take off the presentation, I will. Okay, so let's share the paper. Hold on a second. Okay, so it's this figure over here. The caption does say.
Okay, but we'll refer to. If you go up a little here, figure underneath the figure, so figure 2 shows underneath. If you go below, just
graph convolutional networks and graph convolutional network with residual connections. Our model. So I assume that our model means with diffusion maintains performance at the Leon's increase. Oh, okay. Then it's okay. So this is the figure of range quota. So this is the figure of the increase of performance when you are using higher order integration schemes. Right?
Yes.
I think this is the figure that you are referring to.
Yeah. Okay.
Mm-hmm.
Okay.
So obviously, if you have a higher order one, you will have a greater performance.
Quercus, if you go to the page above figure 2, it says that they're using an RK4 method. Can you go to figure 2?
What? Sorry, let's
figure 2.
Ah.
Yeah,
yes.
figure 2. I think it's high. It's the ranking quota 4, right?
Yeah. Can you go to the page above? Can you scroll up a bit? Yes.
Oh yes, that's correct. Yeah. Okay,
it's
so
high order. Otherwise, all the other stuff are interpreted as Euler forward. So that's the difference. The whole thing is, that's why I like this paper. It shows that the high order actually would give you, or implicit would give you this stability for deeper, because all these neural networks work only for very shallow, but not deeper. So
okay.
So that figure is very important because it shows that you can go. It's not guaranteed, like Nat is probably right about the theory, but at least the experiments show that it's pretty stable with the order.
Okay, I didn't realize about this subtle difference.
That's the most important thing.
Okay. Okay, so let's go back to the presentation. Well, I was just finishing. Hold on a little bit. Yeah, here. Okay, so now, just now Zhen will explain the GRAFF paper, which instead of having the graph neural network training as a partial differential equation, he interprets it as a gradient flow. Okay, So it's an energy-based algorithm, say.
Can I see my screen now?
Yes.
Because you're muted.
Hello, can you hear me now?
Yes.
Okay,
Yes,
cool.
Zhen.
Yeah, thanks. So I'm going to talk about this paper, GRAFF, GNNs and GRAFF S gradient flows. And this is a paper posted on arXiv, I think on October. And this is a very new paper proposed in Michael Bernstein's group. And basically what they do in this paper is that they try to understand the graph convolutions via an energy formulation. And so this paper is actually quite technical. They put a lot of proof, mathematical proof in this paper. And but in this presentation, I will not talk about these technical details and just give the overview of the architecture of the neural network. And if you're interested in the detailed implementation or like the proofs, you are more than welcome to check this YouTube video where the first author of this paper has introduced this paper in much more details. And Quercus has just posted the link in the chat. You can check it maybe after this. And so here is the outline of their contributions in this GRAFF paper. Basically, what they do is they try to approach GNN as learning the right energy functional. So for traditional GNNs, as Quercus talked about, you parameterize the right-hand side of the ODE, or you just parameterize the convolution procedure. But what they do here is they parameterize an energy functional and make sure that the ODE that is satisfied by the GNN follows the gradient flow of such energy functional. And the way they do it is to just to parameterize the energy in a specific form where the gradient flow will look like this. So here is the formula for the gradient flow of that specific energy, which I will talk about later. And so basically here the omega, W, and W tilde will be learnable parameters. And the omega will represent the external energy. I mean, the omega part comes from the external energy of the system, and it characterizes how the node interact with itself. And the second part, which is W, will characterize the pairwise interaction. And the last part, W tilde, will correspond to the residual part, where the input information will directly contribute to the evolution of the system. So here, if we see,
Zhen, can I make an observation? Is this the equation for DPD in some sense, or Morris-Wanswyk? Because it's the first one is the external, the gradient of some potential. The middle one is the time dependent, and the last one is the fluctuations that you're not resolving, the residual, like you said. It's exactly that.
That's very interesting. Then you, but this is not Morris-Wanswyk. You have the kernel, right? But there is no integration.
No, I know, but A bar could be anything.
Yeah, I see. Yeah, very. Yeah, it seems very
time dependent. The residual, and then the potential is the first one, basically. The external. That's the external, actually.
Yeah.
Anyway, I don't want to derail you, but just
yeah, I see. Yeah, that's very interesting observation.
Yeah.
Cool. Yeah. We will check it out to see if we can build some connections. And yeah, so but you can see here the dynamics here is just linear. So there is no like neural network or activation component here. And what they do is that they just simply put an activation function before in front of these in front of the right hand side part, and basically this flow will correspond to their final neural network architecture. And here the A bar will be the normalized adjacency matrix, sigma will be the activation function. So this formula is exactly what they propose in their paper as the GRAFF neural network, GRAFF. And so throughout the whole paper, they will prove theorems based on the analysis on the linear dynamics. So throughout the paper, all the theorems are proved without considering the sigma or the activation function. But what they claim is that the energy associated with the linear system will still be decreasing if they use an appropriate activation function. So that builds a connection to like why they are proposing this and how this kind of nonlinear component will not spoil the analysis. And basically, why they want to do this is because the gradient flow GNNs will have constraints that will result in better inductive biases and reduced number of parameters, so that it can extrapolate better. And here is their motivation. So they compare two different models. One is the graph diffusion model that Quercus discussed at the beginning, and their own architecture graph. So let me explain to you this figure, and I think this is very important. So on this figure, this horizontal line will represent the time axis or the number of layers in the graph neural network. Okay, and this is the y-axis. It will represent the node features or the node attributes. And the information from here is that as time evolves, or as the depth of the neural networks grows deeper and deeper, what will happen in a typical graph diffusion model is that you will see this kind of over-smoothing phenomena, in the sense that a lot of the nodes will collapse into a single node. So basically here in your input, you have 8 nodes, but as time evolves, or as you stack more and more layers, or like they collapse into basically two nodes, and the only information that they obtain at the last layer will be the node degree information. And however, for their graph, their newly proposed architecture, they don't have this kind of over-smoothing phenomena, in the sense that even as time goes to infinity or the layers goes to infinity, you can still differentiate between these nodes. We can see that these blue nodes, they are still different from each other. Yeah, so that's why, that's the basic motivation. And I will begin with some terminology that some of them has already been introduced by Quercus. And so we will use G equals to V to represent the graph. V is the node, E is the age, and A and D will be the adjacency and degree matrices. And also, they use the normalized adjacency matrix A bar to be equals to D negative 1/2 A D negative 1/2. So this is slightly different from what the Grant paper was talking about. They typically only consider the unnormalized adjacency matrix, and for the gradient, they are in graph paper. They are also considering the normalized gradient, and also for the Laplacian, they consider the symmetrically normalized Laplacian compared to the unnormalized one in Grant. And they will represent the eigenvalues of the Laplacian operator as lambda, and the largest eigenvalue, which is rho delta, will be called the spectral radius, and all these eigenvalues are called graph frequencies. Okay, so here is the mathematical formulation of the over-smoothing phenomena in graph diffusion. So they consider a prototypical graph diffusion model, which is the heat equation. So as Quercus has said, we can consider the heat equation as the gradient flow of a Dirichlet energy on graphs. And the Dirichlet energy will take the form of the sum of the L2 norm of the gradients of node features. So if we are considering the gradient flow, we know that the energy will keep decreasing throughout the dynamics. What it says is that as time goes to infinity, this E Dirichlet will goes to 0, or like goes to keep decreasing. And what it means is that this gradient value of x will become smaller and smaller. And if it goes to 0, then what will happen is that this xi over the square root of di will become a constant, where the di will be the degree of node I. And what it means that all nodes becomes very similar. And this is the oversmoothing phenomenon. And here is a typical example of this oversmoothing case, where here I already show you this figure, but on the top side and the bottom side there is like a slight difference, where where we consider, so here we consider the dynamics of x dot equals to a bar x lambda, where a bar is the normalized adjacency matrix, and lambda is equals to this, where basically it stretches in the x-axis and keeps the y-axis not changing. And so we can see from this figure that basically the x-axis will go to a very large number through by evolving these dynamics. So we can hardly tell whether they collapse to the same node or not. So what the information here is that we actually need to normalize x by its norm and plot this normalized version of x to get the correct dynamics, or like to get the correct information. And we can see that this x over the norm of x will actually converge to the kernel of the Laplacian operator. And that is what we observed at the very beginning. So basically this inspires them to propose the so-called LFD dynamics mathematically. So they define a dynamical system initialized at an initial point to be low frequency dominant, or LFD, if the Dirichlet energy of the normalized x converges to 0 as time goes to infinity. So basically this LFD dynamics will correspond to the oversmoothing phenomena, and they prove a lemma saying that if a dynamical system is LFD, then as time goes to infinity, there will be a subsequence such that x will converges to the kernel of the Laplacian operator. And similarly, they propose the so-called high frequency dominant dynamics, where they define a dynamical system to be high frequency dominant if the Dirichlet energy of the normalized node feature will converge to half of the spectral radius of the Laplacian operator. And they also show that if a dynamical system is high frequency dominant, then it will converges to the eigenvector that is associated with the largest eigenvalue of the Laplacian operator. And so geometrically, what it looks like is like this. So this is what looks like as a HFD dynamics, or high frequency dominated dynamics, where the node features will all collapse to a single line, lying on the eigenvector associated with the largest eigenvalue of the Laplacian. And so the specific problem setting they are considered in this paper is the semi-supervised setting, where they consider a set of nodes as the training set and on a single graph, and they consider, for a single graph, they consider some of the nodes as a training set and the rest of the nodes as test set. For the training set, you have some labels, but for the rest of the rest of them in the test set, you don't have labels, and you want to predict these labels on the test set. And there is this kind of separation called the homophily and heterophily, where homophily means that the neighbors will share labels, and the heterophily means that the labels will not be smooth, in the sense that the neighbors will not share labels. So in the first case, which is the homophily case, because the labels are smooth, then the low frequency dynamics will work better. But in the second case, the high frequency dynamics will work better. And so basically, their goal is to design an appropriate graph neural network such that for some of the parameters, or for some weights, the dynamics is low frequency dominant, but for the rest of the weights, the dynamics is high frequency dominant. Okay, so so basically they propose a dynamical system to be the gradient flow of E, such that the x dot equals to the negative of gradient E. And so this gradient flow dynamics will ensure that the E will keep decreasing as time goes to infinity. And these gradient flows are easier to analyze and interpret since X is always minimizing E. And so they will parameterize this E as an E theta, where theta will represent the learnable parameters in the neural network.
Zhen, what is the high frequency here? The upper 1/3 of the spectrum or the upper 50% of the spectrum?
No, so here the high frequency dominant only, I think it only deals with the largest eigenvalue, basically.
Oh, just
so,
okay, very close. Okay, yeah.
So there is a gap basically in this paper that they only talk about two extreme cases. LFD is one extreme case, HFD is another extreme, but they didn't talk about what the dynamics will look like in the middle. So they didn't talk about all the rest of the eigenvalues apart from those that are largest or smallest.
Okay.
Ask another related question. So do they have assumptions on the graph? Like, is it fully connected? Because the eigenspectra will be related to the number of connected components in the graph. So is there some sort of assumption that it's simply connected?
I didn't see that that assumption in the paper. So I don't think it has to be like simply connected.
So you'll have as many zero eigenvalues as you have connected components.
Yeah,
right?
yeah. So this is so there could be like zero eigenvalues.
I mean, there's definitely 1 0 eigenvalue because a fully connected graph is one connected component, right? But especially if you're doing something like with attention where you're learning the weights, right? Like you could get an arbitrary number of 0 eigenvalues if it decouples the graph into different components through the weights. You know what I mean?
Yeah, I got it. So there could be more like 0 eigenvalues, if I understand it correctly.
Right. So just like if you're talking about like the biggest and the smallest eigenvalue, that can become ill-defined here. So it's a little bit dangerous. Probably need to be careful about that.
Yeah, I see. So, but I don't think like that analysis will and that I got your point, but I don't see like they are putting that like fully connected. I mean the connected assumption in their paper.
So, Jen, I had so in the paper they say that for the
Bora,
underlying graph Z.
Bora, you are echoing.
Oh,
can you ask people around to switch up?
Yeah, can you hear me?
Yes.
Yeah, I think in the paper they say for all throughout the appendix they assume the underlying graph to be connected.
Oh, I see. Sorry. Okay. Yeah. Then it should be connected. Sorry, I didn't check that part. Yeah, thanks for the comment.
Yep, thank you.
Okay. So, maybe let me continue. And here, so they first consider a most simple version of the simplest way to parameterize the energy function, which is that they generalize the derivative energy from this the L2 norm of the gradient to be the L2 norm of W times the gradient, where W is the learnable parameter. And so then the gradient flow associated with the derivative energy can be written as basically x dot equals to negative Laplacian x times W transpose W. And here W is learnable. And unfortunately, this gradient flow will be smoothing and still be over smoothing in the sense that the age gradients will shrink to 0, which is LFD. And what they do is they try to generalize from the previous page by rewriting this dirichlet energy. And so what they do is that they first write this dirichlet energy as a sum of two parts. The first part is corresponding to the external energy part, and the second part corresponds to the interaction part, right? And so what they do, what they observe is that for this W transpose W part, it must be positive definite. And they can generalize from here by assuming that they only put a symmetric matrix, omega and W for each part. So in the first part, they replace this W transpose W as a symmetric matrix omega, and then they replace the second interaction component, the W transpose W in the interaction component with another symmetric matrix W. And they can easily parameterize these symmetric matrices by the sum of matrix A with its transpose, right? And so we can interpret this new total energy as the sum of the external energy plus the pairwise interaction energy. And the gradient flow of the above total energy will look like x dot equals to negative x times omega plus a bar xw. And again, this is linear. So they basically rewrite the equation into a nonlinear form by simply putting a residual component and add an activation function in front of the right-hand side. And again, they add another component. Yeah.
Sorry, can you explain the AIJ bar notation and what that specifically denotes?
Yeah, sure. So AIJ bar denotes the I0 and J's column of A bar, which is the symmetrically normalized adjacency matrix.
So that's symmetrized. That's like A plus A transpose or something.
So it's like the formula is actually here. Yeah, so it's here.
Oh, it's normal. It's just normalized by the degree. So they're not working with weights in this. This is just working with the unweighted graph Laplacian. Is that right?
So by the weight, you mean the weight of the neural networks or the?
No, wait for the weighted graph Laplacian.
Oh no. So for this A bar, there will not be weight. So basically, this A will only talk about this A will be the number of the adjacency matrix, right? So it will only be 0 and 1, and you normalize it by the degree.
Yeah, got it. Thank you. Yeah. Sorry for the interruptions.
Yeah, no worries. Yeah, thanks for the clever. Yeah, and cool. So this is the neural network architecture of the graph, and as we say, the first component will denote the interaction of individual nodes, and the second part will denote the interaction between nodes, and the last part will be the residual connection from input. I didn't mention why they add this specific component in the last part. So, but my guess is that probably they need this to further avoid over smoothing in the sense that they still borrow some information from the beginning of the dynamics, so that not all the nodes will become very similar at the end of the day. And they compare their method with a lot of baseline methods. The first one is the so-called linear PDE GCND, which is exactly the same as the generalized harmonic flow, which is associated with the weighted derivative energy. And the second one they compare with is the continuous graph neural network, which is a special case of their graph, in the sense that they basically set the last component, the W tilde to be 0, and the last one is the linear grand, which is the linear version of the grand paper that Quercus just described, in the sense that they didn't consider the attention module for this A. So A is not a function of like xi and j, so it's basically a constant matrix that is learnable. And I think the reason they do it is because they only do like mathematical analysis on linear dynamical systems, so they need this kind of assumption. And there is an informal theorem in the paper saying that all the 3 models above are never HFD, so they will never be high frequency dominant. However, for graph, it will be either HFD or LFD, depending on the nature of the matrix W, which correspond to the interaction part. And if the negative eigenvalue dominates the positive ones, it will be high frequency dominant. If the positive eigenvalues dominate the negative ones, it will be low frequency dominant. And yeah, here comes to the numerical example part. And I already talked about that they will consider the semi-supervised learning training. And for the exact neural network architecture they use, they not only use the dynamical system that I described before, they also use this kind of encoder-decoder type of architecture, in the sense that they first lift their input X into higher dimensions through an encoder, and then use the graph block, which is ODE I described, to evolve it in time. And then finally, they use the decoder to decode the output from the graph block to be the labels. And here in the figure, the processor will correspond to the graph block that I described before as the ODEs. And the evaluation metric will just be the test accuracy.
Sorry, can you speak more to the encoder and the decoder? So if you aren't careful with how to do that, you can make it so that you can't generalize to new graphs of different degree and topology. So is that like an MLP that just maps node features to node features? You know, like if it's an MLP and not a message passing type graph, then it'll be like a graph specific autoencoder. Do you know what I mean?
Yeah, I got it. I think they are not talking about generalization specifically in the experiments that they do in the main text. So as I said here, they're considering the semi-supervised learning in the sense that they consider a fixed graph, and then they basically how should I say, they train on some fixed nodes and then try to predict on the rest of the nodes, but still on one single graph. So I think they use an MLP for the encoder and decoder here. Okay, yeah. So cool. And this is basically what they do. Like they use an encoder phi to map to a higher dimension, and then evolve through the gradient flow, and then use a decoder to generate the output. And all the blue part here will be learnable parameters in the neural networks. And then finally, this is one experiment that they do on a synthetic data set with controlled homomorphy. So basically here, they generate 11 different data sets with different target homomorphy from 0, 0.1, 0.2 up to 1. And they consider 5 different methods, which are GRAFF, GCN, MLP, which is the most basic one, and another 2 ablation study, which is here the prod and neg prod. The prod means that they set the W matrix in the graph to be a positive definite matrix, while the neg prod means that they set the W to be a negative definite matrix, or the negative of a positive definite matrix, which only contains the negative eigenvalues. And from the theory, we know that if the W is positive definite, it will work better in the homomorphic case, while if the W is negative definite, it will work better in the heteromorphic case. And we can see that it is consistent in the numerical experiment results, in the sense that when the homomorphy level is very low, which corresponds to the heteromorphic case, we can see that the prod is not working very well, and also the GCN and is not working very well, because there will not the labels will not be very similar to each other, if even if they are neighbors. So basically, the information is that the graph structure is not very important here. So that's why even the MLP is the best in the low homomorphic case, because the graph structure doesn't mean too much things here. However, if the homomorphic level goes higher, it means that the graph information is more important, so that the GCN and GRAFF will work better. However, the GRAFF or GRAFF, it works better it works well throughout the case. Basically, no matter whether your homomorphic level is low or high, you can always use GRAFF as your model without like changing your model from MLP to GCN. Yeah, and finally, they show their results in some real-world data sets with a different level of homomorphy from 0.11 to 0.81. And so they compare a whole bunch of different methods, and some of them has already been introduced by Quercus before. And so here the message is that they plot the first, second, and third best method through for all these comparisons. And the red one is the best, the blue one is the second best, the purple one is the third best, and it is there. I think it is significant that for their graph method, most of them are within the top 3, and all the baseline methods results was already documented by other papers, so they are not like so most of these results are not done by themselves, but like copied from other competitive papers, so we can trust this result. And finally, we want to talk about the conclusion and possible future directions. So basically, in this paper, they interpret the propagation on graph neural networks as gradient flows, and they use that interpretation to analyze the attraction and repulsion phenomena, which leads to over-smoothing or sharpening effect. And they design new graph neural network architecture based on the energy formulation. But it doesn't say anything about the dynamics that are neither LFD or HFD. So there is still a lot of things that could be studied for the dynamics that are associated with the eigenvalues that are neither 0 or equal to the spectral radius. And also this energy formulation points to more models that are physics informed, so that there could be a lot of other models that could be proposed or studied in the future. And that's all for my presentation. And I'm welcome to any questions for me or Quercus.
Thank you, Zhen. Thank you, Quercus. Questions for both of them?
I've already asked a million questions, so sorry, but I'm going to ask one more. I'm confused about the homophily claims that they make. So like, this is fine as a physics inspired architecture and empirically it works well, but they put in these nonlinear activation functions. So making any claim based off of the eigenspectra, which is a linear property.
Exactly.
Right? It's just, it doesn't mean anything at all. So it's fine to like cook up like inspired by that, by the linear case, they try to cook up this benchmark, but it's kind of meaningless in the actual mathematical, if you want to be formal about it. So,
exactly.
And a lot of the stuff in both of these papers, I just heard both of you say a few things about how much rigorous math there is in this and so on. It's like all over the place in these two papers, right? That there are some things that are like to a 0th order approximation rigorous, but not once you actually go into the implementation. So I just want to put out a warning. We actually lost about to this paper. So yeah.
Yeah, I totally agree in the sense that they didn't consider what will happen in the nonlinear dynamics, and I guess probably it will be much harder to analyze. So that I guess that's why they just use the linear analysis to act as an inspiration for the overall architecture. But I agree with your argument.
It is super interesting though. So the fact that they have a dissipate, like George was mentioning about the connection to DPD, the fact that this is inspired by structure preserving reversible and irreversible dynamics make it that you would hope that it could, in the nonlinear dynamics, you could find a latent low dimensional attractor. Right. And it kind of seems like this is what they're dancing around in this slide, right? Like you're finding a low dimensional manifold that your data lives on, and that working with the reversible and the irreversible stuff helps you parameterize that. But formally, I don't think there's anything here.
Yeah. I see. Yeah, thanks for the comment.
Zhen, did you have a chance to look at the gating graph neural network of Mishra, the G2?
So I just look at the abstract, but I haven't got the chance to go into the details.
because Mishra was claiming that even the graph is over smoothing, and that the G2 actually, which is the latest paper of the series with Mishra and Bronstein. So I don't know, maybe you can bring it up so people can see it, and then Nat or other people.
Yeah, sure, definitely.
By the time Zhen opens the paper, I just want to tell you all that I shared the link of the Crunch Group YouTube channel on the chat. I would welcome all of you to subscribe to our channel, and we keep on putting videos of the Crunch seminar over there, so you would get a notification immediately.
And I want to add to some data. I would say that if we go over 1,000 subscribers, then we'll get money so we can finance our Wednesday free lunches.
No choice, we plan to add another day. We actually are planning to add Friday.
Well, then we have to have income. Yes, so Nat, this is the paper, the just leave like that. Yeah, this is the paper. I haven't read it myself, but Mishra, I was talking to Mishra yesterday, and he said that this is actually improving the graph, not the grant. Yeah, see here the multi-rate flow of message passing, as opposed to maybe two, high and low. I think that's what they're separating now, because the spectrum is the spectrum is continuous, so those would be.
Maybe we could have him give a talk and present it.
Yeah. I was wondering, Panos, are you online? I think I saw him online. I don't know if he.
I'm here. Yeah.
Did you see if there is, this repulsive, attractive? Zhen, can you go back to that comment that you had about sharpening and smoothing using repulsive or attractive forces and?
Yes. Like here?
Overall, there is an eerie similarity, and also there's some dissimilarities with the Morris-Wanswyk. So,
yeah, I'll have to look. I mean, I heard your comment before, but I didn't have the chance to understand what are the different terms there. So, but I would like to look it up. I think also Nat made a comment about something about the equation 10.
Yeah, in the paper, you can see it. They don't have the random fluctuations, although of course you could do a random walk on a graph,
right?
Which is an interesting idea. But if you look at equation 10, they have the attractive, the repulsive potential, and then the dissipative one. And it's the same kind of simplified form. There's no kernel in there, although you could pull the kernel into the weight of the graph.
Yeah.
But it's like exactly the same.
I have a way, I'm not going to reveal it online, but I think I know how to let's say, control the rate of over smoothing. I'll tell Zhen later.
Okay, that would be great.
Are there more questions for Zhen and Quercus? Or maybe for our first speaker, Leonard? Okay, so if there are no more questions, thank you everyone for tuning in today for these two wonderful talks that we had from our department. And we would share the link of the YouTube video update on the email that for everyone who is subscribed there. Thank you and have a good afternoon and a good rest of the day. Thank you.
Right.
Thank you. Bye-bye.